Hello, it's February 24th, and I'd like to welcome all of you to this week's New Paradigm for Mankind. My name is Megan Beets, and I'm joined by my colleagues Ben Deniston and Jason Ross. Mr. LaRouche has been very emphatic in the recent weeks that history is not being determined in the transatlantic. The leadership of history now lies in Eurasia. And this is typified most prominently by the actions of President Putin in the strategic policy, especially his intervention into what would probably already have erupted into world war centered in the Middle East and in Syria. We also see this in a very important aspect in the leadership of China and their commitment to the cause of humanity, the cause of the development of the human mind in the solar system with their lunar program. And there was an announcement, people likely have heard, there was an announcement in January of this year that China will land a lander and probably a rover on the far side of the moon in 2018. Now, this is not a replication of something that the US or the Russians have done. This is something which nobody has ever done before. And on that mission, they plan scientific experiments, including very low frequency radio antenna to detect frequencies that we've never detected before. So you have a real commitment to the idea of the growth and progress of humanity and saving humanity from World War III coming from the leadership of Eurasia. That's the future. That's where mankind is going. History is not being determined by this dead, powerless transatlantic system, which is typified under this British puppet Obama by war, by the financial collapse we're seeing in Wall Street and in the European system, by the shutdown and the attacks on the American space program, especially by Obama, who in 2010 canceled the US manned spaceflight and lunar program, the Constellation program, and replaced it with lies, budget cuts, etc. So the United States must join this new paradigm. We must join the paradigm we're seeing in Eurasia. And what that requires, which is our topic today, is a recommitment, well, a rediscovery and a recommitment within our system here to real science, a rejection of what's been a 100-year or more paradigm of rot of Bertrand Russell, the replacement of science and thinking by logic and mathematics. And to do that, the example we'll reach back to today as a launching point is the example of Einstein, whose name has been in the news very prominently in the recent weeks with the detection of gravitational waves, something which was discovered and forecast by Einstein 100 years ago. So with that, I'll kick it off to you guys.
Thanks, Megan. Well, I think as we've Jason covered some of this in the Friday webcast, this detection of these gravitational waves. So we wanted to take some time today and dig into that a little bit more, because I think this is exciting on a number of fronts. And I think this can get at some of the real core scientific questions that we really want to tackle here. But as Jason referenced on Friday, this is really kind of a detection, not a fundamental discovery. This is something that Einstein thought should likely be a consequence of his fundamental discovery 100 years ago. And now we're technologically catching up to the kind of the boundary conditions defined by the scientific discovery of Einstein. I think it's also important to root this in the work of Riemann. Here you have Einstein and Riemann, intellectual buddies. This comes out of Einstein's general relativity, and in his general relativity, he showed that space-time is not flat. It's not Euclidean. It's not just a flat Euclidean space out there. It has a certain curvature to it, certain structure to it, and that structure is physically defined. And this is something that Riemann really said is going to be the frontiers of science, looking to geometry, our conceptions of space and related notions being not a priori, not determined just by a priori notions of geometry, especially not a priori notions rooted in certain sense perceptual conceptions, but they're going to be physically defined. They're going to be defined by actual physical processes. things the human mind has to discover, not stuff you're going to deduce from a priori geometric conception. And, you know, in a very real sense, this is what Einstein showed us with his general relativity. Space-time has a structure to it, has a structure that's shaped by the activity of mass, gravitating bodies. That gravity is an expression of the structure of space-time. And one consequence of this, Einstein was able to reason, was that if you have certain changes in the relations of gravitating bodies, maybe two bodies orbiting each other, or bodies moving in certain ways, or any rapid change in mass, certain conditions could create certain propagating effects in space-time, so-called gravitational waves. And so now this was just detected. Now you have, you know, on the one side you have this as a confirmation of Einstein's discovery, which is good and exciting. On the other side, it also opens up a new window, a new avenue towards investigating the very nature of the universe. And as people are probably generally aware, all of our knowledge of the universe comes, you know, it's the universe outside the Earth. You know, all of our observations of our solar system, for the most part, you know, we've sent things a couple places, but, you know, our galaxy, other galaxies, structures in our galaxy, these all come from readings of the electromagnetic spectrum, variations of light. You know, so people are familiar with the electromagnetic spectrum we have displayed there. You can see the visible section that we're so intimately connected with and tied to is just a small slice of this much larger range of types of light, electromagnetic radiation, electromagnetic emanations. And when we look in different ranges, you know, we can see different structures. So this is an example I've used a couple times. This galaxy, the image on top is the combination of radio observations and optical observations. On the bottom, you can see, in the optical, you see what looks like what they call an elliptical galaxy, fuzzy blob, large galactic structure. It's a decent sized galaxy. It's, you know, it might look small in that picture, but that's a lot of stuff going on in that little thing. But when you look in the radio, you see that this galaxy is also associated with this very fascinating structured production of these jets and lobes, these large structures of plasma shooting out of the very center of this galaxy, something you just wouldn't see in the visible. And, you know, this is a total surprise. This is not something that was expected when radio astronomy started. They started looking, and no one expected to see radio waves emanating from places in the sky, much less start to see structures like this. Anyways, that's been, you know, all of our observational capabilities have been associated with expanding and improving resolution and time resolution, different things, but improving our ability to observe across this spectrum and do it in better and better ways. But the gravitational waves are different. It's not just another part of this spectrum. You know, maybe just a simplified analogy for people. You know, imagine if your only sense perceptual interaction with the world around you was just seeing the color green. That was it. All you could see was green. You know, if you're outside, maybe you see some green leaves just floating in the sky, just floating, because all you see is the color green. And then over time, maybe you develop new capabilities to start to extend the colors you can see. So now you start to move maybe into the yellow, into the red. You start to open up new colors, and like, oh, those aren't just green floating things. They're actually part of this other structure, this tree trunk. You know, move into the blue, into the violet, you know, and you start to open up the whole visible spectrum. You know, it's kind of like what we're doing. But then all of a sudden, say you, for the first time, are able to then start to hear things. Well, that's not just more of the spectrum. That's a totally new sense, and it gives you a totally new dimension to investigating the nature of the world around you. It's a different type of emanation, different type of propagation of the effects of certain processes that you can now interact with. And I'm going to come back to that, because I think the most important thing, you know, that we have to really, I think, to emphasize on this is the work of Kepler, Mr. LaRouche's insight into Kepler's work in terms of the relations between sense perceptions and actual knowledge. And I think this is a very good case study to get into that. So that's what I want to conclude with. But to get into that, I think it's worth looking at what we now are, even in this very first, we can hear for the first time, but we can only hear even in this small window. We've only heard one thing so far, at least what's been published. I think maybe they've been detecting more things, but saying it's worth looking at. I think this is, to me, fascinating, and I think it really opens up some new dimensions that really need to start to be looked at more intensely. But what did we hear? What do we detect in the gravitational waves with this signal that the LIGO system picked up? And this is the published representation of the signal, the gravitational waves that they detected with the two different detectors. Comparison of what was actually observed with what would have been expected if this was a certain type of process that they were looking for. And on the bottom is another representation of this, where you can see there's a certain frequency in these gravitational waves that increase it. It starts to rapidly increase with time. It's indicated on the bottom. So we have some frequency of gravitational waves that were detected. And then they had a certain rate of change of that frequency, culminating in a certain point and then changing. So what was this? What would have caused this particular frequency that was detected by LIGO? And according to the published results, this is something that's been looked for decades. This is something people have been looking at and studying. According to the published results, they think that they can tell just from this frequency and the rate of change of the frequency how much mass must have been involved in creating this particular signal, in the amplitude and in the frequency in which it was detected, and how that mass changed and interacted with the orbit. So from this, again, these changes in the structure of space-time are a result of mass and changing position of mass and acceleration or orbiting of different masses. So they think from this signal, they think this must have been two objects, something on the order of about 30 times the mass of the sun each, orbiting around each other. And then orbiting around each other and getting smaller and smaller orbits until they actually merge. So that's pretty wild, 30 times the mass of the sun. But then if you know that, if you can say that the mass is these two objects creating this gravitational wave signal is on the order of about 30 solar masses each. We also know the frequency, so we know the period in which they're orbiting each other, which is, it got up to an incredibly fast pace here. 75 orbits a second, I think, was the peak. So it's pretty damn fast. We orbit the sun, we don't orbit at 75 times per second, right? I mean, that's incredibly fast. But having now an idea of what the period of the orbit is and how much mass is involved in the system causing the orbiting, that also allows them to say, well, what's the approximate size of the orbit? How far away are these two things from each other? And this is where it really gets remarkable, because they, according to the reasoning they've presented on this, it's on the order of something like a couple 100 kilometers. So we're talking about objects, something on the order of 30 times the mass of our own star, orbiting each other in something in the range of measured in hundreds of kilometers, and doing it at a speed, at a rate of 75 orbits a second, which would translate to something like over half the speed of light, which is mind-blowing.
Just to say 75 times a second in another way, that's 4,500 RPMs. So if you imagine, your engine spinning when you're driving on the freeway, except if it was 200 kilometers across, that's pretty fast.
I don't think we make those engines yet, but so then 30 times the mass of the sun, orbiting in the range of a couple hundred kilometers. What's the radius of our own sun? Our sun is 1 solar mass. It's got a radius of about 700,000 kilometers. We're talking about objects of 30 solar masses acting in a domain measured in the hundreds of kilometers. So when you work these considerations through, you're forced into a very interesting domain, which is a certain superdensity or hyperdensity, which is generally associated with what they call black holes. You're talking about now a regime where, according to the evidence and according to how it's been interpreted and understood, this points us in a direction where we have the amount of mass, a certain amount of mass concentrated into a certain small enough volume that starts to approach or enter the domain, which is generally discussed as these so-called black holes. So this has been discussed as actually the best evidence so far for the actual existence of some phenomena like this, some phenomena of this type, the so-called black hole. We've seen certain things. I'll get into a little bit in a few minutes. Certain bodies orbiting other bodies that indicate that could be what's going on. But this is actually the best evidence we have that there are things out there where the amount of mass is concentrated into the small enough volume that's associated with this black hole point. So what is that? What are these black? And I think it's worth just being kind of precise on the language here, because this is really, I think, a very clear and obvious boundary condition in our current knowledge. I mean, it's literally a singularity in the mathematical physics and the equations. It's literally a point where the equations you would use to try and describe gravity and space-time at these points, they literally go to infinity. They break down. They can't tell you what's happening there. And that's actually where this concept of these black holes in general relativity first came about, was just by analyzing the equations. People were able to show very early on, before we had any idea these things might actually exist out there, that you could get, under certain conditions, you could get this singularity point where the things kind of break down. And since then, that's been a subject of intense mathematical speculation and theorizing, and what if you had this and that, and what if you introduce quantum mechanics? And there's been extensive amount of work in a whole range of theoretical speculation, just trying to work from the standpoint of the current mathematical understanding, which I think obviously has some limits, because this is where our theory breaks down. So to think you can just resolve this by working within the current mathematical framework, I think presents obviously a clear fallacy here. And I think the assumption in even going down that track, is this whole Russell assumption that that ultimately we'll be able to resolve the entirety of the knowledge of the universe as a consistent mathematical framework from what we already know. I think that's in general the type of assumptions involved in this whole orientation to try and solve these things from the standpoint of our current knowledge. And there's a lot that can be said. There's attempts to so-called unify gravity and quantum mechanics and come with a grand theory of everything. And the black holes are actually a great subject, or a subject of intense investigation pertaining to that pursuit. But the whole assumption of that pursuit is that you can come to some kind of mathematically consistent resolution to understanding what's happening here from the standpoint of our prior knowledge. That it's possible to deduce or come to some conclusion from what we currently know, from what we currently understand about our current description of the universe. I think there's another track, so when we say black holes, that can have a lot of meanings. It has a certain meaning just in terms of the initial presentation of this being a possible thing out there. It's got certain extended speculations as to what these things are the further you travel down this kind of mathematical descriptive framework. So it's there's a whole range of what could be meant so it's kind of a loaded term. So what we know from these observations now, there seems to be something which approaches some of those conditions in terms of the mass confined into a certain volume. What that is, we don't actually know. And I think it's worth posing another track of investigation as to a real way to investigate what is actually going on in these types of processes. This is maybe taking one additional step away from the particular investigation that we have with the LIGO. So with the LIGO, we saw the evidence for these objects on the order of like 30 masses concentrated into a very, very small volume, indicating it could be one of these so-called black holes, whatever those are. There's another similar phenomenon that's been investigated, and this is something we discussed in the recent galaxy class series, which are these so-called supermassive black holes. So things that are, again, thought to be this black hole. Exactly what that is, we don't know. I don't want to imply that, you know, this is a full endorsement of some of the more wild and speculative theories about what some people think these things might be. But there's something of that effect that's vastly more massive than just a few tens of times the mass of the sun. So these are actual observations of stars orbiting something at the very, very center of our galaxy. And by the way these things are orbiting, it implies to us that whatever's causing those stars to orbit this very central point looks to be on the order of 4 million times the mass of our sun. So these are these so-called supermassive black holes. Really massive, supermassive, you know. So we see pretty good evidence of this, something like this operating at the very center of our galaxy. We see these operating, we have indications that pretty much at the center of every galaxy, we have some of these phenomena, these supermassive objects at the very, very centers of these galaxies. But things get really interesting when you start to look at what do we know about these things from the standpoint of observation. Well, one, they're not just super massive, they also are associated with incredibly energetic and active activity. Here's another image of a galaxy, again, combining the different wavelengths. So the very, very center, kind of the white or yellowish, goldish blotch in the very, very center is what you would see in the optical range only. So that's an entire galaxy there. So that's a very, very, very large structure at the very center there. When you look in the X-ray, you can see it's surrounded by a activity that's emitting in the X-rays. And then as we saw in the earlier image, in the radio, you see these jets shooting out from the very center. And these jets are thought to be large structures of plasma, large plasma structures. So you have something in the very, very, very center of this galaxy producing these structures that dwarf the entire size of the galaxy. And this is thought to be associated with these this thing that's called the supermassive black hole phenomenon in the very, very center of the galaxy. So we have evidence for incredibly energetic and structured activity being produced by this, supermassive singularity point associated with the breakdown of our current understanding of mathematical physics, where our understanding literally breaks down. You can take this further. You have the work, I don't want to get into too much detail on this. You have the work of the American astronomer Halton Arp, recently passed away, also an Armenian astronomer, Victor Ambartsumian, who presented a very interesting and extensive case indicating that these centers of these galaxies associated with this super energetic central point, associated with this singularity point, the breakdown of our current understanding, appear to be associated with potentially the creation of new galaxies. In the work of Arp, showing that these appear to be associated with the creation of what might be according to his interpretation, he certainly presents an interesting body of work that is certainly worth consideration, further study. That these could be the production of what I call baby galaxies, proto-galaxies, with certain anomalous characteristics in their redshift. Something I don't want to get into a lot of detail on, just given the time, but there's the production of certain cores that could be the seeds for the development, the growth of an entire new galaxy, which display a certain characteristics that we just can't explain with our current understanding of physics, with their intrinsic redshift effect. Einbart Sumian was looking at something similar in terms of the creation of new matter, new energy emerging out of these cores of these galaxies. And right away, this would be a violation of the conservation of energy and matter as we currently understand it. Another indication there's something going on in these things which is outside of our current ability to understand, to explain. So these things, these singularity points, especially these ones in the centers of galaxies, appear to be a key point of study if we want to come to a new, higher level of understanding of the universe. And a higher level understanding that we would only come to through real human discovery, not just trying to resolve current inconsistencies within physics in a kind of deductive framework. So this is fascinating because LIGO, made this first detection, which appear to be, two of these supermassive object or super dense objects orbiting each other and interacting and producing a certain characteristic signal in the effects on the space-time, which we're interpreting as produced by that interaction. But this is really just the beginning. Again, this is like opening up a whole new sense, sound, similar to sound in a sense. It's been, people have been looking at this for a long time. They've recognized that there should be a whole spectrum. So, maybe somewhat similar to the electromagnetic spectrum. Again, you have shorter, longer wavelengths, processes that emit certain wavelengths, certain processes emit in certain regions, other processes emit in other regions. So you have a whole, it's not just one thing you're looking at, you have a whole range of stuff you're looking at. It's thought, it's expected that we have a very similar thing in this gravitational wave domain. The LIGO falls at the high frequency end. It's a terrestrial interferometer, as identified here. So it's something on the ground that's used to try and detect very high frequency changes in the gravitational field, these gravitational ripples. And those are thought to be produced by certain processes on certain scales, again, like stellar mass, black holes orbiting, interacting, those types of things. And there's also investigations to look in other ranges of the spectrum, like by going into space, where you can get a much larger separation between your detectors, allow you to detect much lower frequency fluctuations in the gravitational field, things that might be associated with larger objects, larger processes, such as maybe the interactions of multiple of these supermassive black holes, for example, is something that is is being investigated here. So, just to give kind of a tease the imagination a little bit, we're really opening up an entire new sense, an entire new domain, where types of processes that might be very difficult or maybe impossible to detect or investigate in just the emanations given in the electromagnetic spectrum might now be detectable, investigated in this domain of gravitational waves. So this is, a very exciting prospect now being opened up. But I think, just to come around to how we want to look at this, I think Mr. LaRouche's work reflecting on Kepler, and especially in the last few years, he's developed and presented, I think, a very interesting thesis I think is really what needs to be put up front right now for considering how to approach this. And Mr. LaRouche elaborated, in some great detail, reflecting on Kepler's discovery process, Kepler's own way he thought about his discovery process, and in particular the way Kepler thought about the relation between sense perceptions and actual discovery, actual knowledge, and the role of different types of senses in maybe presenting one track of evidence or another track of evidence, or one type of shadow and another type of shadow, but recognizing that, yeah, we want these different senses, we want these different types of detections out there. We want to develop those so we can have more clues, more evidence, but knowledge doesn't come from any of those detections alone. You're getting different shadows, but where do you get the capability to understand what's causing those shadows? And Kepler was very clear in recognizing that none of that comes from the sense perceptions alone. It comes from something that the human mind can uniquely do. And he had really a beautiful presentation of this entire thesis conception in his Harmonies of the World, where he developed this conception of harmony as the ability of the human mind to come into it to itself generate conceptions consistent with causality in the universe. But that process isn't mediated by receiving a sense perception and just operating on the basis of what that sense perception is alone. It's mediated by the process of the mind itself being stimulated to generate something the human mind can do uniquely, which is then consistent with the organizing processes of the nature of the universe more generally. And he himself, I think, in a very beautiful way, recognized that this is part of a much longer fight over the nature of science and the nature of mankind. You can't really separate those, and the nature of the universe. Going back to Aristotle and Plato, he recognized very much that this was his conception of this was consistent and a development on Plato's notions of recollection or remembrance. The idea that discovery, the generation of real knowledge, real ideas there's a certain potential already there in the human mind, and it's something that can be stimulated to almost like the mind's remembering something it already knew. The knowledge doesn't just come from direct interpretation of what's presented, but it's something that the human mind does. Versus Aristotle, who had this conception of the blank slate, that knowledge is just what's written upon the mind directly through the senses, which as Jason's discussed, is very consistent with his views about what mankind really is, the political system, slavery. I think it's a very much a connected process in recognizing the nature of man, the nature of the human mind, and the role of the human mind in the universe. Really comes to one conception. So Kepler, he came out of this current, and obviously the key player in the development of Kepler was Cusa, who had his own reflection back to Plato and certain developments upon Plato's conceptions. So you have this continuity of this train of thought, this kind of epistemological fight. What's the nature of knowledge? Is knowledge just sense perceptual interpretations, or induction or deduction from sense perceptions? Or is knowledge actually something uniquely generated by the human mind? And what does that then say about the nature of the human mind and causality in the universe? And I think that's the challenge before us today. With these gravitational waves are great. We're going to be able to get new clues, new shadows, new emanations, as Kepler called them, reflecting certain activities, certain processes going on. But we're not going to get actual knowledge of cause and principle just from those sense perceptions, just from that new perception alone. We might have a great new opportunity now to combine them, to look at the certain processes emanating in the electromagnetic spectrum, also emanating in the gravitational spectrum. We might get interesting clues that we can now compare and contrast. But again, it's only going to come from those shadows teasing the mind to come to some new discovery, which is really going to be the only way we can resolve these questions. And I would posit get beyond this current boundary condition expressed by our, our current limitations of the nature of the universe. And one, I think, very interesting example again is these, whatever the hell these black hole things are, especially when considered on the scale of these supermassive objects. So anyway, and just to bring it back around, just because he's somebody who obviously had an insight into this, and we're still catching up with him today. But to come back to Einstein on this, I just always have been remarkably struck and feel obliged to continue to come back to a certain conception he presented in terms of the nature of knowledge, this epistemological fight. This was actually not on general relativity, but this pertained to the question of the quantum and quantum mechanics, and a certain fight that was going on around the nature of causality, and certain indications that what you might call a mechanical or a mechanistic conception of causality appeared to be breaking down in this, certain quantum processes in the very small. There's a lot can be said on that, but I think this is part of a dialogue, a discussion between Einstein and Max Planck. It's presented in the end of Planck's book, Where is Science Going? And when posed this question about, well, what do you think about the breakdown of causality? Some people are saying, well, then causality just doesn't exist. Causality is this kind of mechanistic interaction of things, one thing causing another, maybe in a kinematic type effect. That's what causality is. That was what's assumed and presented. So now that that fails, what's the deal? What do you think? And this was Einstein's response. He said, now I believe that events in nature are controlled by a much stricter and more closely binding law than we suspect today, when we speak of one event being the cause of another. Our concept here is confined to one happening within one time section. It is dissected from the whole process. Our present rough way of applying the causal principle is quite superficial. We are like a child who judges a poem by the rhyme and knows nothing of rhythmic pattern. Or we are like a juvenile learner at the piano, just relating one note to that which immediately precedes or follows. To an extent, this may be well when one is dealing with very simple and primitive compositions, but it will not do for the interpretation of a Bach fugue. Quantum physics has presented us with very complex processes, and to meet them, we must further enlarge and refine our concept of causality. So, a lot can be said about Einstein and his work and his thoughts, and I'm not going to present myself as an expert on Einstein, but I think, if you just look at what he's saying here, it gives a very clear and impressive insight into where he thinks we need to go to resolve these questions. It's not that causality doesn't exist. It's that the universe isn't organized in the simple conceptions of causality that we've been assuming, we've been presenting. Maybe not dissimilar from the notion of the curvature of space and time. That it's not that the way we might tend to interpret the nature of the universe, causality in the universe, from the standpoint of the way we think about it from our sense perceptual interaction of how things seem to work. That's the flaw. That's what we don't want to go down. But if we want to know more, what do we have? We have what the human mind does. That's what enables us to know things about the universe. That's what tells us about the universe, and that's what really tells us about how the universe is fundamentally organized. So he's saying, if you want to understand the quantum, let's start trying to think about causality the way a Bach fugue presents causality, not in a linear A to B to C sequence, but, as he said here, the whole process. What's the organization of the whole process? And not just trying to dissect, an A to B interaction in that process, abstracted from the whole thing. So it's a little quote. I would like to see more of his thoughts, in these directions. But I think this is clearly a reflection that he is absolutely a self-conscious part of this continuity in this fight over science, recognizing the primacy of the role of the human mind in science, in opposition to the sense perceptual track. So anyway, I think this is what we should be celebrating right now about Einstein, and this is what we need to bring back, not just put his name on a T-shirt and be a fanboy or something, but actually really fight to understand how he thought about these things and bring science back to the direction that he was fighting for, and really that has gone dramatically away from him. So
I think it raises a very important point about economy. I mean, the basis of, in terms of its relevance today, the basis of our ability to have an economy is that, unlike animals, we can discover causes. We can know how the universe operates. And when we abstract what the mind brings to that, we end up with a sort of artificial intelligence view of what science or understanding the world is. We end up with an inductive one. More to say on that, because let's look where does Einstein, who does he look back to as well? I mean, one thing, very directly and explicitly to Kepler, but you had mentioned Riemann, whose work on physical geometry really put the nail in the coffin on the approach of Euclid, where people would try to approach the shape of space from the shape of space, from shapes, from geometry itself. And Riemann said that no, the understanding of space has to come from another world altogether, not from mathematics, not from geometry. It's got to come from physics. What are the physical principles that give rise to the way things interact with each other? And that interaction is what we call space. And that's exactly how Leibniz expressed space.
Mm-hmm.
Leibniz said there's no absolute space on its own. It's not an existing thing. Space is a relationship between concurrently existing things. How do they relate to each other? In terms of different locations, etc. That's where space comes from. Riemann, in some of his work, looks back to what made modern science possible. And he points right to Leibniz and the calculus, not as a mathematical tool, but as a physical concept that brings an entirely different domain into mathematics. To say something about that, look back to Kepler. Kepler discovered how the planets moved. In doing that, he had to overcome the language that astronomers used, which expressed orbits in terms of shapes, which expressed motions in terms of geometry, in terms of things that could be expressible and understood mathematically. Kepler, in his great work, The New Astronomy, whose full title says, A New Astronomy Based on Causes, was confronted with the fact that he didn't have a language that could express that. And Kepler said, the planets change their speeds based on how close they are to the sun, because the sun is the cause of that motion. That's a principle that changes at every moment. The planets would have speeds that changed at every moment. There's no shape, no mathematics, no geometry that could account for that. That was a physical cause. That was a principle. So Kepler did what he could with that. Leibniz really brings a certain closure to what Kepler was doing by introducing the infinitesimal calculus, where the differential, the world in which the cause that expresses itself as the perceptible changes that we then see, is given a reality. That differential is a real thing. So no longer do we have observations that are tied together by changes among locations or times or different observations that we make. Leibniz is, with what he's done, not added something to mathematics itself. He's really dedicated, he's laid something down about the reality of cause of that other domain, which Kepler knew of, tried to express. Leibniz developed a metaphorical language to make that possible, and which Riemann, in his work on these subjects, pointed back to, saying, this is the thing that really made science possible. We're able to go down into the infinitesimally small and recognize that causes exist, and that's completely changed our understanding of all physical processes. Something makes them happen. Everything that occurs is a result of something that's causing it to occur. So that's not just math. That's something that's very serious. On what you had said about Aristotle and the blank slate, to go back to Leibniz again, another person Einstein was very fond of, Aristotle or John Locke, who had said that the mind is an empty slate and experience writes upon it. The trouble with that both is that, yes, it denies the mind developing and bringing something to the table, creating new ideas, as opposed to drawing generalizations from observations. The other aspect of it is that inductions draw generalizations in terms of the perceptions.
Mm-hmm.
That is, inductive principles express themselves in terms of effects. There is no opportunity for a cause that exists in a different domain, so to speak, to really be something that composes the universe. And, to Leibniz, that opportunity to say that nothing occurs without a reason, why so and not otherwise, that no effect takes place without a cause giving rise to it, that that's something that we need to bring back in our understanding today of what science is and of economics, both because economics is based on the ability for us to develop scientific and cultural principles to transform how we relate to the universe, and also because economics is a science. In other words, economic results follow from economic principles being applied or not. Economics is a science. It's a science that Lyndon LaRouche has made his own personal discoveries in, and is the basis of his and his movement's ability to lay out perspective for where we ought to go today. And we should keep in mind where the base of where that ability comes from.
Mm-hmm.
So we can take the opportunity of this, what did you say? Not a discovery, but a
detection.
A detection, right? It's an opportunity. A reminder, right? It's an opportunity to really take things all the way
mm-hmm.
to the top of where we can go beyond, gravity per se itself.
Mm-hmm. Yeah, it also goes to Mr. LaRouche's focus on the inseparability between what people might tend to separate in the domain of science and the domain of culture or art. There's a unity in human creativity specifically, and that is the fundamental issue we need to return to: the recognition of the existence of a principle of human creative capabilities. What is that exactly? We don't really fully know in terms of ability to explain it away in fully or anything, but recognizing that is whatever capability we have that separates man from animals. It enables us to come to these discoveries, and as Mr. LaRouche developed in his science, that it's also the causality enabling mankind to increase the economic potential, he defined the potential relative population density. That whatever that creative potential we have, that is our key to understanding the nature of the universe more generally. And that was the Renaissance conception, and that's the conception needed for the new Renaissance we need today.
Okay, that's a good place to leave it for today. So thank both of you very much. I'd like to thank all of you for joining us. Stay tuned to LaRouchePack.com. Is a recommitment, a rediscovery and a recommitment within our system here to real science, a rejection of what's been a 100-year or more paradigm of rot of Bertrand Russell, the replacement of science and thinking by logic and mathematics. And to do that, the example we'll reach back to today as a launching point is the example of Einstein, whose name has been in the news very prominently in the recent weeks with the detection of gravitational waves, something which was discovered and forecast by Einstein 100 years ago. So with that, I'll kick it off to you guys.
Thanks, Megan. Well, I think as Jason covered some of this in the Friday webcast, this detection of these gravitational waves. So we wanted to take some time today and dig into that a little bit more. I think this is exciting on a number of fronts. And I think this can get at some of the real core scientific questions that we really want to tackle here. But as Jason referenced on Friday, this is really kind of a detection, not a.
Hello, it's February 24th, and I'd like to welcome all of you to this week's New Paradigm for Mankind. My name is Megan Beets, and I'm joined by my colleagues Ben Deniston and Jason Ross. Mr. LaRouche has been very emphatic in the recent weeks that history is not being determined in the transatlantic. The leadership of history now lies in Eurasia. And this is typified most prominently by the actions of President Putin in the strategic policy, especially his intervention into what would probably already have erupted into world war centered in the Middle East and in Syria. We also see this in a very important aspect in the leadership of China and their commitment to the cause of humanity, the cause of the development of the human mind in the solar system with their lunar program. And there was an announcement, people likely have heard, there was an announcement in January of this year that China will land a lander and probably a rover on the far side of the moon in 2018. Now, this is not a replication of something that the US or the Russians have done.
Space and related notions being not a priori, not determined just by a priori notions of geometry, especially not a priori notions rooted in certain sense perceptual conceptions, but they're going to be physically defined. They're going to be defined by actual physical processes, things the human mind has to discover, not stuff you're going to deduce from a priori geometric conception. And, you know, in a very real sense, this is what Einstein showed us with his general relativity. Space-time has a structure to it, has a structure that's shaped by the activity of mass, gravitating bodies. That gravity is an expression of the structure of space-time. And one consequence of this, Einstein was able to reason, was that if you have certain changes in the relations of gravitating bodies, maybe two bodies orbiting each other, or bodies moving in certain ways, or any rapid change in mass, certain conditions could create certain propagating effects in space-time. So
this is something which nobody has ever done before. And on that mission, they plan scientific experiments, including very low frequency radio antenna to detect frequencies that we've never detected before. So you have a real commitment to the idea of the growth and progress of humanity and saving humanity from World War III coming from the leadership of Eurasia. That's the future. That's where mankind is going. History is not being determined by this dead, powerless transatlantic system, which is typified under this British puppet Obama by war, by the financial collapse we're seeing in Wall Street and in the European system, by the shutdown and the attacks on the American space program, especially by Obama, who in 2010 canceled the US manned spaceflight and lunar program, the Constellation program, and replaced it with lies, budget cuts, etc. So the United States must join this new paradigm. We must join the paradigm we're seeing in Eurasia. And what that requires, which is our topic today,
fundamental discovery. This is something that Einstein thought should likely be a consequence of his fundamental discovery 100 years ago. And now we're technologically catching up to the kind of the boundary conditions defined by the scientific discovery of Einstein. You know, I think it's also important to root this in the work of Riemann. Here you have Einstein and Riemann, intellectual buddies. You know, you have this comes out of Einstein's general relativity, and in his general relativity, he showed that space-time is not flat. It's not Euclidean. It's not just a flat Euclidean space out there. Has a certain curvature to it, certain structure to it, and that structure is physically defined. And you know, this is something that Riemann really said is going to be the frontiers of science, looking to geometry, our conceptions of